Thank you. So I will present our work on the compressibility of the Jovian magnetosphere. And so let's start to see what is special about this magnetosphere. When we talk about magnetospheres, and especially the case in Earth, we refer to the region in space where the magnetic field of the Earth is dominant, and we usually approximate this with a dipole. So the magnetic dipole works quite well for Earth, but it's not appropriate for giant planets like Jupiter and Saturn. The reason is, well, one of the reasons is that inside these magnetospheres, we have additional plasma sources. For the case of Jupiter, we have the volcanic moon of Io, which creates a small, in terms of thickness, plasma torus, as you can see in this artistic image on the right. And a more realistic picture would be, also getting input from observations, to consider something that deviates from a dipole. In that sense, this image is a little bit misleading towards the center because it looks like a dipole, but as you go further outside, you can see that these nice magnetic field lines that you encounter in the case for the Earth are no longer there, but are stretched. The reason is that in giant planets, the magnetosphere includes some very strong azimuthal currents that enhance the field and make the magnetic field lines stretch outward. This is what we call a magnetodisk because very close to the equatorial plane, you have this elongated disk-like structure. A model to try to recreate this structure was proposed by Caudal in 1986, and it was quite recently implemented in a code by Achilleos et al. To give you a brief overview of this scheme, Caudal scheme is a very simple model. It's a 2D axisymmetric MHD case, and you can recreate the magnetic field of the planet in coordinates starting from the planet to the magnetopoles and also to the spin axis. For simplicity, the spin axis and the magnetic axis are considered aligned. Now, the magnetopause is where all the forces included are at equilibrium, and the major forces in our case are the magnetic force, the J cross B, the pressure gradient, and the centrifugal force. We usually neglect gravity because it's only important very close to the planet, and at very large distances, it quickly becomes very small. Since we are dealing with an axisymmetric magnetic field model, we can express the magnetic field using the Euler potentials. In other words, we can rewrite the magnetic field as a cross product of these two gradients. And what is different also in the magnetospheres of giant planets, we have a hot plasma population, which means we have particles with thermal energy much larger than the kinetic energy due to the rotation. If you take all of this into account and also put some constraints from observations regarding, for instance, the density, the temperature, and the composition of the plasma, and also prescribe a velocity profile that can be either based on a dipole, which is Hill's method, or you can be more robust and try to update it using the magnetodisk profile, which is what we are doing. If you put all of these together and you start iterating from an initial condition, you can get a very nice description of the magnetodisk. Very briefly again, in order to create this nice magnetic field profile, you can start with a dipole. You can start expanding the magnetic potential using Jacobi polynomials. Fortunately, since you're using axisymmetric MHD, you don't have to worry about the second magnetic potential. It's just a constant perpendicular to your coordinate system. And you can keep on iterating until you reach a threshold level that you're satisfied with. And you can see on the left panel, an original solution from Caudal. On the right is our own recreation. And just to show you how much a magnetodisk differs, you can follow the solid lines. And very close to the planet, the solid lines and the dust lines, which are the dipole, are very close together. But as you move radially outwards, you see there is quite a big difference between the two. So this is something that must be taken into account to fully account for a global image of the magnetosphere. Now, what is the compressibility? With the term compressibility, we collectively include how the magnetosphere responds to any changes. This can be internal or external. Obviously, the most important external changes are due to the solar wind or any changes in the interplanetary magnetic field. But also in the giant planets case, like Jupiter and Saturn, the hot plasma pressure or other internal processes are also very important to consider. If you want to calculate the compressibility of the magnetosphere, see how it changes according to one of these factors, what you have to do is calculate or have observations, ideally, of the magnetopause distance as a function of the, let's say, the dynamic solar wind pressure. Unfortunately, we don't have so many observations. So what we did is create a big number of models, just like the one I showed you before, including the magnetodisk, and try to use them as actual observations, or as we call them, crossings of the magnetopause. We created an ensemble of over 700 cases, each one with their own unique magnetopause radius and hot plasma population. So we covered a very wide range of radii, so from very compressed magnetosphere to very expanded states, and also a very high range in hot plasma population. So for very quiet states or extremely disturbed states. Since we are only modeling the magnetopause, we have to come up with a solution to actually calculate the solar wind. To a very good approximation, what you can do is say that the dynamic pressure of the solar wind is the same as the magnetic and the thermal pressure exactly given by the model at the magnetopause. However, you need to account for deflection, because as the solar wind hits the magnetosphere, it doesn't completely travel at the same direction, but there is a deflection that goes, let's say, around this nice oval shape. So this is accounted for. And if you look at the plot on the right, where is the distribution of our models, its color represents a specific value of the hot plasma index. So different states, in other words, of the magnetopause. Since this is a log-log plot, you can see that it seems to be a linear behavior between, not between, but basically for a specific choice of hot plasma population. But what we wanted to see is this linear behavior appropriate for the whole study, or does the system size of Jupiter play a role in that? To make the hot plasma population contribution a little bit more clear, I show you two different states in terms of hot plasma population: a moderate or an average state in terms of activity, and a very active state, so a lot of hot plasma population. And here I show how its component contributes to the total plasma pressure. So I plot the pressure for the cold plasma, the hot plasma, and the magnetic pressure. And if you focus on the right line, you can see that if you include, obviously, many more hot plasma particles, the contribution from the hot plasma becomes very significant and very close to the cold plasma. So this is something that you really need to keep into context. So the million-dollar question is, of course, what is the relation between the magnetopause distance and the dynamic pressure of the solar wind? The very easy way to solve this is, as I said before, try to find a simple linear fit. In other words, assume that you have a very constant compressibility index and see how the system behaves. And if you make this calculation for different values of the hot plasma index, you see you obtain values around 3.5 and let's say 4.2, which are typical for the magnetopause of Jupiter. But however, you can go one step further. Assume that you don't have a constant compressibility index, but rather this compressibility index is a function of the pressure itself. This has already been done in the case of Saturn, and we applied this additional method here, considering a parabolic and a generalized fit for this problem. And this is what we get. So the solid lines are the parabolic method. So there's a second order dependence of the compressibility index to the solar wind, and the dotted dashed lines are a generalized fitting method using a hyperbola, basically. Now, if you average, if you follow one of the curved lines and you take the average along the whole magnetosphere, the average value is indeed the one given by the linear approximation. So in that sense, the linear approximation works well. An extra step is to see if you can, since we have a very big range of radii to consider, if you can somehow make a scaling. And in our case, we found that this can be done if you take the local plasma beta and you average it throughout your ensemble and use this effective value to calculate the solar wind pressure. We found that for quiet and moderate states, so for states with very low KH index, you can indeed find a very nice linear profile to scale all your models. However, this breaks down if you go to very disturbed states, so for KH indices beyond 10 to the 7th, and then it's no longer valid. So I mentioned, I talked also about Saturn. So let's see what are the differences between the two planets. On the left, I selected 3 of my cases, and I just present the linear fit, which seems again very adequate for our research. If you now do the same work for Saturn, like Ariana Sorba did back in 2017, you see that the linear approximation is not valid, but rather you have 2 very distinct areas. You have a different slope for expanded states, so for very large magnetopause radii, and a different for a compressed, so very low magnetopause radii. This is something that, at least at the linear scale, we do not observe in Jupiter. So, going to my conclusions, what we wanted to do is study the compressibility of the magnetosphere in Jupiter using an ensemble of models with different parameters as artificial or virtual crossings. We found compressibility index values that were typical and meaningful for the system, so very close to 4. And we found out that the linear analysis was sufficient for moderate states. However, if you want to consider the whole magnetosphere, effects of the system size start to kick in, and you necessarily need to apply some high order analysis. One of these cases is to just try to scale with the effective value of plasma beta or solar wind pressure, but still this is only approximately correct for very quiet states. If you want to examine the system in detail, you really need to apply a second order scheme, and then you see that for more expanded magnetospheres or for larger magnetopause radii, your system can be easily compressed. And the dependence on the hot plasma pressure, however, remains similar to the one for the Curonian magnetosphere. In other words, if you increase the hot plasma content, also the hot plasma pressure increases, and then the whole force balance towards the end of the magnetopause changes, and it's easier actually to contract your magnetosphere. Okay, that's it. Thank you.